Up the road from Microsoft Research, who's going to talk on verifying crypto protocols written in C. Andy.
Thanks, Nigel. Great, thanks very much, Nigel. Okay, this is Amanda Gordon. This is joint work with Francois, who's actually just walked in the door, a PhD student at the Open University who's been working with us at MSR Cambridge, and also Misha Aizatulin, who's also a PhD student at the OU who's been working with us at MSR Cambridge, and also my colleagues Jan Jurins, who jointly supervises Misha and Francois, and Dave Naumann. Okay, so what I would like to do is to describe our project on looking at cryptographic software in C and describe where we've got to and suggest some future directions. And I'm going to, eventually when I get to an example, I'm going to describe a particular simple request-response protocol and show how we can analyze it using two different methods, one based on symbolic execution, another based on interactive verification. But this is a broad workshop, so I wanted to start with a bit of background and motivation about why we're trying to do this, and say a little bit about the trajectory that got us where we are today, which started a long time ago, actually funnily enough in this building, with process calculus, and got us down to the functional language F# and eventually on to C. I mean, we're just generally, I mean, we're looking at the problem of finding bugs in cryptographic protocols. And when we started in the 90s, there were hardly any automatic techniques or formal techniques for doing that, and so we came up with various ways of representing cryptographic protocols using process calculi, and then that eventually, so they weren't programs that you could run, but they were programs you could sort of think about and do calculations about, and eventually that led us to, or the community, to various automatic techniques, and then on to actually the step of wanting to actually verify code that could actually run and interoperate with other implementations. And in fact, there's going to be a bunch of talks at this workshop that about very recent work on large protocols. But what I'm going to focus on in this talk is C. But since this is a mixed audience, I start with a glossary. So if all this is standard to you, forgive me, but I don't think it's standard to everyone in the room. So during the course of this talk, I realized when I was going through my slides that I was making glancing mentions of various techniques from formal methods and program verification and static analysis. So I'm going to try and explain those when I come to them, but I thought it might be useful at the start, particularly for those of a cryptographic background, if I just put a few words up just to give you some context of the kind of techniques that we use in verification. So first of all, static analysis. So what's that? Well, that's the idea that you might have a bit of a program text, and without actually running or testing it, you want to do some sort of analysis on it statically, i.e. before it's been run, to find bugs or maybe to find problems with performance, but generally to find bugs or to prove correctness. And these ideas go back to the 70s. So the symbolic execution is a very simple idea that you run the program statically in the absence of the concrete data you're eventually going to have, and in place of the concrete data you have various algebraic variables that represent inputs that haven't arrived yet, and you can compute on them, and instead of having concrete bit strings, say, you end up with algebraic expressions describing what has been computed so far. And that was King, 1976, introduced symbolic execution, and a closely related technique due to the Cusos is abstract interpretation. Symbolic versus computational. So this is an abstract to the workshop, so you probably are aware of this, but I'll just briefly say it. That in the cryptographic community, of course, there's a range of, so to speak, computational ways of reasoning about cryptographic protocols, where one thinks about the attacker as being a polynomial bounded probabilistic Turing machine, and the protocol is sort of under their control. In the formal methods world, it's not until fairly recently that's been we've had techniques to deal with the computational model, and instead we've relied on symbolic, also known as Doliviau models, where we think about the expressions that come up during a cryptographic protocol as being terms from some symbolic algebra that can be interpreted as bit strings, but one doesn't actually do that. One just thinks about the thing as being an algebraic term and manipulates it. Process calculus, what's that? Well, that goes back also to the 70s, a classic decade for computer science ideas. So process calculus, introduced by people like Tony Hoare and Robin Milner in the 70s, were a way of reasoning about concurrent systems. And in fact, way before there really was very much concurrency in computer science. They had these algebras or calculi that could represent concurrent systems. And one of the famous ones was the pi calculus that introduced this idea of name restriction, which was the idea that within this sort of small process calculus language, you could generate a completely fresh name. So this is exactly, well, it's very close to the idea of generating a fresh key or generating a fresh nonce. So some of us figured out that you could apply process calculus to cryptographic protocols. And I can't resist mentioning SPI, which is now ancient history, but Martina, who's sitting at the back there, and I invented the SPI calculus as a way of taking the Dolomieu abstraction and bringing it into process calculus. And we invented it here. The first conversation was at a drinks reception at a workshop like this back in '95, a long time ago. So if you were wondering whether or not you should go to the drinks reception, you know, if you value your career, I would say go to it. Who knows what happenstance conversations you might have. But since then, there's also been the applied pi calculus that generalizes it. Now, okay, getting on to proofs, which is the subject of this, we've got a range of different automatic and not so automatic provers. So there's a bunch have been invented specifically for the purpose of reasoning about crypto protocols. Things like Proverif, which reasons in the Dolomieu model using process calculus, and CryptoVerif, which reasons in the computational model also using process calculus, and EasyCrypt, which is a more recent gadget that I think Gilles will probably describe in his talk at the end of the workshop. Now, these are generally speaking entirely automatic. On the other hand, so if they work, it's fine. If they don't work, it can be a pain to persuade them to prove something. On the other hand, there's a class of general purpose provers that from the start are intended to be interactive, and the user will provide proof hints in various ways using various languages to guide the theorem prover to actually prove some mathematical proof. And in fact, Robin Milner was also heavily involved in this back in the 70s. And so the one that has been mostly applied in cryptography is Coq, which has been sort of fostered by INRIA for, I don't know, 30 years or something. Maybe not quite 30 years, 25 years. And it's now a very substantial system with, you know, a whole lot of different mathematical libraries and some great sort of scalps in the form of big theorems like the four-color theorem, you know, on its belt. And we use that, and we're going to mention that in this talk. And then on the other hand, there's also automatic provers, but general purpose languages, things, and sometimes known as SMT solvers, which means satisfiability modular theories. And these are generalizations of SAT solvers for propositional logic, generalized to allow quantifiers, and also generalized to allow things like arithmetic or bit string manipulation or algebraic data types. And some of the famous ones are YICES and Z3, that's a typo, Z3. Now, you're getting actually to code, which is the subject of my talk. We've had a range of, we started off a long time ago in process calculus, but then moved to functional programming languages, because they're much easier to reason about than imperative languages, because in functional languages you don't explicitly manipulate state. And so a lot of the difficulties of C, which we've had trouble with, actually, like manipulating pointers and explicit allocation and deallocation of memory, and the kind of basic absence of a type system doesn't arise. And so we did some work 5-6 years ago on starting from OCaml or F# programs, and then analyzing the various ways. And we had a system called FS2PV that took F# programs and translated it Proverif. So you could actually, in a sense, you could run your Proverif models. And we did a bunch of big examples. And INRIA, the MSR INRIA Center, they did a version of TLS. And then more recently we did F7, which is more like a more general purpose in a way than FS2PV, and it uses something called refinement types to represent properties of programs. And we've done a lot of work with F7 on sort of more modular reasoning about F# programs, and that's led to other languages, Fine and F*. And then on C, so so when we started this project on C, we were aware there were a number of provers in existence for C, and we wanted to see if we could retarget them, take some of the knowledge we'd learned from using things like FS2PV and F7, and kind of teach C provers to be able to reason about crypto protocols. And so I put up 3 there: VCC, Very Fast, and Frama-C. And these are all provers for Hoare logic, which in Hoare logic is the idea of well, which is this idea here that if you've got an imperative program with each function can be annotated with a contract, which consists of a precondition and a postcondition, and the preconditions and postconditions are formulas that are assumed to be true before you run the program, and formulas that must be proven by the prover to be true after you exit the program, and by program I mean the particular function. And it's quite convenient to have something called ghost state as well. So what's ghost state? Well, this is the idea that you take the program you want to reason about, and maybe there's some information that you want to remember that you wouldn't normally include in the program. So a typical example is a log of events. So if you write a program and it's sort of sending various messages over a network, you want to remember what has happened. Now you wouldn't normally record that information, but for the purposes of verification, it's very handy to do so. And so what you do is you introduce a new state in which you deposit that information. And this is ghost state in the sense that it's present, but it has sort of ethereal. It doesn't actually affect the control flow or any of the data in the concrete program. But it's there, and because it's present, you can mention it in preconditions and postconditions, as you'll see. Okay, so that's a sort of lightning tour of formal methods. Any questions at this point? No. Okay, so let me get onto the talk proper. So, standard motivation. Cryptocode is hard to get right. There's a stack of. I think this audience is. I think you're familiar with this idea. You know, just every year there's sort of a raft of new problems. Sometimes brand new design, conceptual problems. But also there's just a rehearsal of problems we knew about before in other contexts get repeated in the setting of different protocols. So we've had for a long time models of cryptographic protocols, but they have not been linked to the actual running code, and it's the running code that matters, that has to get patched at great expense. So you really want to have techniques that can reason about the running code. So that's what we've been trying to do. So this is this is a summary slide of trying to. I'm putting this up, not that I want to go into all the details of it, but to sort of outline where we were about, I suppose in 2008. So this is when we had spent several years using F# to write reference implementations of protocols, and meeting with some success. Building up quite a few case studies. So the lovely thing about this room is that it's got a stick. So the concept here was that we wanted to be able to write protocols and applications using the protocols in a high-level language in F# or OCaml, and then verify them in various ways. And what this chart is showing is the different kind of things we could do to the same code. So the simplest thing is we wanted to actually run it. So we would plug in concrete crypto libraries and network libraries, compile it with a standard compiler, and then we could run it and we could interoperate with other implementations of the same protocol, say, and convince ourselves that the protocol that the code we were modeling, or the code that we were studying, actually corresponded to a runnable version of the protocol. Because you don't want to reason about a bit of code that doesn't interoperate with anything else. It's not so convincing. And then we had various pathways where we could compile down to F#, down to eventually to FS2PV, going down to ProVerif, or down to F7, and then that was refinement type checking using Z3, and we could also go to CryptoVerif. In fact, there was a path going from F# down to CryptoVerif. And by we here, I wasn't involved in all this work, but this is a big collaboration with myself, Karthik Bhargavan, Cedric Fournet, and Cedric had led a lot of people at the MSR INRIA Center who'd done a lot of this work, and in particular they'd done some really big case studies. We did card space at Microsoft, but they did an even bigger case study of TLS 1.0. So we'd achieved we'd shown that these methods would scale up to large chunks of F# code, and this work has continued, and Cedric, I believe, is speaking about a much enhanced version of this case study on TLS 1.2 later in the workshop. Still, I was, you're very conscious that the crypto protocols aren't generally written in F# or ML. It would be nice if they were, and it's certainly it's way better using F# than abstract models, because you can actually run them. But at the same time, various people convinced me that most of this stuff is written in C. So let me see. So I don't want to speak about that. So we decided that we would we'd push on and see if we could actually take these techniques and apply them to C. I gave various talks about this, and Jan contacted me and said he wanted to be involved, and we got a couple of students, Misha and Francois, who are at the back, and we cracked on. So what I'm going to do now is get down finally to some details about what we did. So let me start by talking through a simple protocol. And this is a simple request-response protocol, and the idea is that both parties share a long-term session key, a long-term protocol key, and in the first message, the first party is going to send his message encrypted under that key, and also include a fresh session key to be used to send back the response. And I'm assuming that the crypto concerned is authenticated encryption. Here we go. So this is what happens if you run the code. The client starts off saying he's wanting to connect to a particular port. He wants to send a particular request. He wants to use the session key, and then he sends this blob on the wire. And then the server is listening, he accepts the connection, he gets the same message, he receives the authenticated request, and then he authenticates the session key, prepares some response, and then sends it back. Okay, so that's what you'd see if you ran it. If you wrote it out as a protocol narration, it would be like this: A sends to B his identity together with the encrypted request together with the session key, and then we use the session key to send back the response. So this is nice, and you can discuss that, but we need to get it into some form that we can actually verify. So we need to have, so before I get onto the C implementation, let me speak about what the actual protocol model would look like in ProVerif. So if you haven't seen it before, this will also serve as a lightning introduction to the sort of Dolov-Yao style of representing crypto protocols. So what I'm going to build up is a model of that protocol in the process calculus implemented by ProVerif. So the protocol's up there. So we start off, we need to represent the fact that messages will be sent on a public channel. So we say free C to say that there's a free or public channel called C that the attacker can monitor, but implicitly also the participants are going to send the messages on this channel. And then what about cryptography? Well, as I say, we're going to use an algebra to represent the cryptography. So I need to introduce the function symbols of the algebra. And there's a couple for symmetric authenticated encryption, big E and big D. So E is for encryption, and D is for decryption. And E is declared just as a fun, meaning there's no particular rewrites applying to E on its own. So it's what we call a free algebra. And then D is introduced by this declaration that says that if the D symbol is applied to a key, a term actually, that's interpreted as a key, and you give it a term that's the encryption of the same key under X, then D will extract the plain text. And that's the only thing you say about D. Okay, so that's the only way you can. It's the only thing you can do with D, and moreover, it's the only way you can get at the contents of E. I mean, we can compare two terms for equality, but we can't do we can't like extract the contents of like X, or indeed modify it without knowing the key K. One can come up with more elaborate models, but this is a nice simple one to be going on with. Then we also have, there's also a certain amount of sort of syntactic infrastructure, sort of formatting that's in the protocol, because here we have a pair of things that are encrypted together, and the top level message, in fact, is an encryption, is a pairing of a principal identifier together with a ciphertext. So over here we have a binary constructor called conc1 that is used for constructing data, and it has operators first and second. And first gets out x0, and second gets out x1. And we declare this as data, which means implicitly the attacker is actually able to look inside a conc1. I mean, so there's additional rewrites given to the attacker to enable him to extract the contents of this thing. So I should say, in this whole way of modeling, the idea is that we're going to program up the explicit behavior of the client and the server and any other participants, or well-behaved participants in the protocol. And we're also going to describe what keys they know, and describe what operations they have. I mean, what underlying crypto libraries they're making use of in an algebra. But we're not going to say anything about the attacker. The attacker is just an arbitrary program in this language who is able to monitor data on a public channel. and rewrite on it using these operations as he or she wishes. So the security theorems are usually phrased in terms of, for all attackers, something positive is said about the system composed with the attacker. Okay, so what about the system itself? So we have a couple of definitions. Let A, this is A, and this is B, and in fact the whole system down here is given by this process. And bang means replication, meaning you've got an arbitrary number of copies of the replicated party running in parallel. So it's like an array of replicas of A, an array of replicas of B. And we also, new is this operation from the pi calculus that makes the fresh key that is known just to A and B, and it's not known outside. So the attacker is sort of notionally running alongside here, and he doesn't have access to the key, but he does have access to C. So he can see messages being sent on the wire, but he can't see he can't actually get at that key itself, unless for some reason it gets compromised. And so we can, other things being equal, the attacker doesn't get the keys, but you can also program in the possibility that particular keys get leaked by causing code within the scope of the restriction to output the key on the channel, on a public channel like C. Okay, and then this code here just goes through and implements the behavior of A and B. So so here we have an event. So this is the kind of thing you might put in a log file or go state. But in the process calculus, you just think about it as being a notional event. And so there's an event that the client is wanting to send a particular request, and then further on, after he's received a response back, he's going to have an accept event that says that he thinks that the decryption of the response under the session key was associated with this request by the server, and on the other hand, the server B has an event indicating that he's replying. So he receives a couple of messages and he decrypts them appropriately, and then he says, okay, I'm going to make up a new response that I'm going to use to reply, and then I have an event that associates the response with the contents, what is extracted from the first message. And then we have the code that actually processes the messages. So we start off with making a new session key, and then we pair together the client ID, which is like A's identity, together with an encryption under the long-term key of the concatenation of the request together with the session key, and that gets sent off on the public channel, and then we get messages back off the public channel, and then we try and decrypt the second message with the session key we created. And this blocks if it's the wrong key, and otherwise we believe that we've successfully got a response back from the server. And then similarly, we can code out the behavior of the server. And then we can run proverif. Takes a little moment. So we see we're running up there. We say proverif, and we've got a particular input in PV model out, and we grep for results. And I hope you can see this, that we got three successful outputs from proverif. The first thing is the sanity check. It's very easy to write models that don't work at all, right? Do nothing, because the formatting is wrong. And in that circumstance, sort of nothing happens, right? So and everything is sort of vacuously secure, and you think you're happy when in fact, it just didn't work. So the first thing we say is it's not the case that you can't reach client accept. So client accept is down here. So the first thing is just showing that it is possible for A and B to run together in the presence of an opponent and get to this event here, meaning you can get to the end. So it's a live protocol. And then we have some correspondence assertions that will say that basically speak about the authenticity of each of the two messages. So the first one is saying that if the server actually replies with a couple of variables, then it was, send the second message, then it was the case that the first one of them was sent by the client. And the second correspondence says that if the client eventually accepts two variables, then they were the ones that actually had been sent by the server. Okay, so if there's glitches in this protocol that meant that there could be confusion where the client would accept a message that hadn't been sent by the server, or maybe been sent with respect to a different message, then these correspondences would fail. Okay, so this is the kind of thing, maybe 3 years ago you'd have to write by hand, and we wanted to get to the point where we could generate these from C protocol code. So this is the direction that Misha took in his dissertation, using symbolic execution, this idea from the 70s that you could run code with symbolic variables in place of inputs from the network. He took that idea and said, let's see if we can apply this to C code and extract protocol models. And I thought it was impossible, but he proved me wrong, so good on you, Misha. And so in fact, the proverif code I just showed you was automatically extracted using Misha's code from the C code of that protocol. So here's an outline of how it works. So there's several pipelines, several stages in the pipeline. We start off with C source. We use something called SIL to parse C, and so we and then having well, we use SIL to not just parse it and rewrite it so that a run of the protocol actually keeps a log of all of the trace of successful instructions. So then we have so in this step we rewrite and do a concrete run of the program and log all the instructions that were executed, all the receives from the network, all the tests of whether whether keys are equal or nonces are equal. All that sort of stuff is logged in a long trace of the execution, and so then you get something like this where you just have a series of instructions that have been logged. And so here you've got a call to encrypt, for example. And then the next step is symbolic execution of that concrete trace. So we're guiding the symbolic execution by a particular concrete run. And a big assumption in this work is that for most or many crypto protocols, there is one kind of standard, well-behaved, compliant run that the parties go through, and if they deviate from that run, it's an error. So that applies to this protocol. It applies to a lot of protocols studied in the research literature. It applies to things like TPMs. It doesn't apply to everything. It doesn't directly apply, say, to anything that has any error recovery in it, because then you've got multiple passive execution. So the idea is we're going to track this one run, and then once we've traced the concrete version of it, we've discovered it. And the lovely thing about that is it's almost automatic. You just run the thing, and you get this trace. We then symbolically execute that one run, thinking about it as a sort of long, concrete program. So if you go into the TLS, you can do trend cycle. That's right. So there were difficulties in scaling this up to things like TLS. Yeah. So then we've got this concrete run. We do the symbolic execution of it. And at this point, we can actually we symbolically keep track of the state of the memory at each point, and I'll go into a bit of detail in the next slide about that. But then, having done that, during the symbolic execution, we can actually output a process that represents the behavior of this program, in particular in terms of the inputs it makes and the outputs it makes on the network, and also any actions like encryptions and decryptions, and also formatting operations like concatenating byte arrays and so forth. And you automatically get code like this that represents all of this, so that you've got a new operation where a key gets generated. We do put asserts into the code. So the main annotation you have to put on the protocol code is to add assertions that we want that we need to use to specify our security properties. So then you also have like formatting, where you've got concatenations of byte strings and substring operations on byte strings and taking the length and so forth. But notice what we completely got rid of is all the memory model, right? So that was one of the difficult things about manipulating C, but we've got no more pointers or pointer arithmetic, any of that sort of stuff. We've just got a representation of the data that's been manipulated. So in a sense, after a bit of a detour, we're back to almost like an F-sharp program, if you like. So that's good, but this is still not analyzable. So then we can do a bunch of rewriting where we look at the formatting and try and get it back down to a sort of $Yow style process calculus term, which is the one I was showing you earlier. So this is what you get, and now we can run proverif on that. And we can, and that gives us verification in the symbolic model. And in some circumstances, proverif also gives you results by standard soundness, by computational soundness arguments, gives you results in the computational model. So for some of our examples, we get those results. So a bit more detail. How does it work? So here's a program for sending the request. This is A trying to send a request, and he's got a bit of context where he's got state for this particular protocol that includes things like keys and identities of the parties, and requests and so forth. And line 1, the first thing we do is compute that m1 len is to be this, is the length of the whole message. So we do a calculation. During symbolic execution, what happens is we keep track of, so we don't have the concrete data, instead we just have variables representing the potential data that will be present at runtime, and not just data from the outside world, but also data that's in our state. So after executing line 1, you get this, we have a symbolic stack, this is symbolic state that corresponds to the program. So after executing line 1, on the stack, we've got a variable m1 len that has this symbolic expression. So this is what I mean by symbolic expression. So it's not I mean, at runtime, this would be a particular number, but during the symbolic execution, we have an algebraic term. And then we malloc something of size m1 len and put that into the variables p and m1. So after executing that on the stack, p and m1 are pointers into the heap at a new variable called heap 6. And heap 6 itself, eventually, after doing a mem copy, has got the variable p in it. And p now has got the address of heap 6. So these addresses here represent things these are pointers to things that have been malloced in C state, right? And so C state, or the heap in C has got a set of chunks of memory, each of which has got a size, and generally speaking, pointers point, well, not always, but pointers may point at the start of each of these chunks, and you can have an offset, and a pointer will be somewhere within the chunk. So we can represent that by having a variable like heap 6 that represents the start of a chunk of memory, and then you have an offset. So P and M1 are at offset 0, but say stack P after you've done this plus equals 1 there. So a bit of pointer arithmetic, P ends up being a pointer into heap 6, but at offset 1. And we just continue in this vein. So we symbolically execute this code, and then over here we build up a symbolic representation of the heap. And then at crucial points, such as here, where we actually send something on the wire, so we send, so this is the code that will send the message on the network. Sorry, this is the length. It's the first thing we send is the length of the message. The second thing we send is the actual message. But anyway, the first guy is going to send the message. So we drop some IML output code, or process, that we're going to analyze eventually. That's an output on this public channel C that I've been speaking about, together with a symbolic expression, which is representing the length, which is calculated by looking at the full len, right? So by the time you get to line 19, full len has got this symbolic expression. So that's the thing that you output. So we're.
Is that why in the programming you have this funny two sends and receives, even though you're only receiving one?
That's well spotted. Yes.
But you
one of them was the length.
But you don't do anything with the length that's brought in, yeah. So you could. So what happens if the code sends the wrong length and then the receiver generates the wrong amount of buffer and then?
Well, I suppose you could say the analysis checks that it does actually allocate enough. Okay, so that's the rough idea of the analysis. Okay, so then just to summarize some of the results. So we did a paper at CCS last year about this, and we had 5 examples. So CSUR is a classic in this area. So the first people to analyze C implementations of crypto protocols were Perrin and Gubola-Rek in about 2005, 2006. And they had a 600-line implementation of 1/2 of the Needham-Schroeder-Low protocol that they were able to verify for security correctness. This technique actually found a memory safety error in CSUR because we're actually checking how much is being allocated and checking there's enough. We also looked at a range of other protocols, RPC, Needham-Schroeder-Low, and also a smart metering protocol. And we were able to get some verification results in most cases pretty efficiently. In the case of smart metering, we discovered a flaw, which is a classic kind of C error. So this is code that allocates a session key that's so many bytes. And the way it actually gets used is that the session key is a a star char, and so we dereference that. We actually want to get the whole, whatever it is, 8 bytes. But, or rather, sorry, the first 4 bytes, I suppose, the first 4 bytes of this long key. And what this code does is to dereference this char, which gets a single byte, and then casts it to unsigned int, which would be 32 bits for 4 bytes. And this is basically just 0 extends it. So, so he's trying to pull 4 bytes out of memory. He gets 1 byte, and 0 extends it. And so it's a bit of a disaster. And then this code was, this code was used both for the sort of sender and the receiver. So the error wasn't discovered by testing, but by using symbolic execution, we're able to sort of discover that the generated code was off.
What is again the problem that you can detect? So this is a cast of a char to an unsigned int.
Yes.
This is not a problem, but
well, in itself, but then when we actually looked at what the code was doing, it was summarizing what it was doing. We discovered that there was this bug.
So you found this bug by hand, or
well, by using the tool, yes. It wasn't that it. Yes. Oh, Misha's going to respond. Misha.
Yeah, just to make clear, this encrypted reading is something you send on a network. So the idea is you have a reading of the meter, which is a 4-byte integer, and you would like to XOR it with a key to protect the secrecy. What really happens is you XOR it with a key which has 3 of the bytes equal to 0.
Mhm.
So you're sending 3 out of every 4 bytes unencrypted on the network. That's what
Right.
Okay, and we have some recent work where we're targeting cryptographic instead, and this is basically taking the project much further, and this chart is showing for a slightly larger set of examples that we're able to generate proverif models. These are actually harder to analyze than proverif models, so we had a bit of work into that. And you're seeing here the sort of size of the models you're getting, that there's a certain amount of sort of handwritten libraries that are necessary for the particular crypto primitives that are being used in the model, and then the red stuff is what is automatically generated from C. And at this point, we believe we're sort of leading the pack of those who are verifying C crypto codes, in that no one's been able to verify as much as 3,000 lines of code before. And we discovered another bug during this analysis, different from the ones I spoke about. Okay, so a bit of summary before I switch to the second direction. So model extraction by symbolic execution. So the great thing is it's almost automatic. You have to annotate libraries to indicate how particular operations like encryption are to be abstracted in the Dolomieu algebra, but apart from that, it is mostly automatic. It does make this big assumption that we follow a single correct run, so that means it doesn't apply unchanged to some larger realistic or large-scale protocols, but we're working on that. So in a twisted sort of way, this is be twisted to people from the point of view of process calculus, that these are tools that let you write pi calculus code in C, which appeals to me a little bit. So verification shows our model is correct, but because the code may follow other paths, it doesn't directly verify the code in all ways. And we've got some future directions I mentioned here. Okay, so a second direction is to use these interactive verifiers I mentioned earlier, things like VCC and Verifast and Framacy. And this is the PhD work of Francois. So I'm going to talk about the same protocol, but a slightly different specification using events and assertions. And also I'm going to say a little bit about the possibility of key compromise as well. So the way we model key compromise is having events that represent the key. So bad AB means that the key that's shared between A and B has gone wrong. Okay, so you can start once the model explicitly allows key compromise, which of course is possible in the real world. You have to modify your security properties because you have to take into account there might be compromise, but you want to be able to say things like, even if some of the population of users has compromised keys, if two principals are well behaved and their keys are not compromised, then they still obtain security. So we're able to do that by qualifying, by having sort of limited qualified record of compromise like this. And the other thing about this is that we're in this version of the protocol, I'm going to have events will be logged in ghost state. Remember this sort of ghostly stuff, the state that kicks around in the program and doesn't actually directly affect concrete execution, but is used for specification. And then I'm going to have assertions, program assertions in the C code that would say here, for example, that after you receive this request, that if B checks it, then it's either the case that the request exists in the log, has happened, or the key has gone wrong. Because if the key has gone wrong, then the attacker could fake this message, and you could get to this line without this having happened. And similarly, you have an assertion here that with a qualification. Okay, so the puzzle is how can we use some of these nice tools that we developed for reasoning about C code to do crypto proofs. And our strategy was to take a theory of crypto that we developed in the context of F7, one of these tools for F#, and port it to VCC. And we tried to develop the theory for F7 in a way that was sort of independent of the particular programming language you would use to do the crypto. And the way we did that was we had we generated an abstract type of symbolic terms that could arise in the protocol, and then also made an inductive definition, a sort of logical definition of two predicates, level high and level low. And level low means that this is a term that could arise during the protocol run and be known to the attacker. And level high means this is a term that might arise during the protocol run and would be known to the well-behaved principles. And it means that it could not. So low terms are high because low terms could be input by the well-behaved principles, but it's not the case that high terms can safely be sent on the wire. So now we hit some problems. You know that C has concrete byte arrays and has no abstract types, so we couldn't directly take what we've done in the setting of F#, which used abstract types, and use it in the setting of C. So our strategy was to have another ghost table. So we have a ghost table to represent events that have occurred during the protocol run, but we also introduced a ghost table that sort of keeps track of what you could call the sort of $Yao assumption, or the symbolic crypto assumption, which is a ghost table that keeps track of all the symbolic terms that have arisen so far, together with the concrete bit strings that they correspond to. And our assumption, or the $Yao assumption, has always been that you don't get collisions, that you can't have this happening. You can't have two, if you encrypt, you can't have an encryption of two distinct, or a key and a message, or a plain text arriving to the same bit string. So that's fine in the Yao theory, but in practice it's not true, of course. But we make the assumption this happens unlikely, relatively, or I suppose we make the assumption that we're trying to rule out attacks that don't make use of these collisions. So if ever any collisions arise, we just abort and say that's fine. So the security results you get with VC are saying, provided no collisions occur, there's no way the attacker can fake can cause the users to get confused about identities or to give up secrets and so forth. So then, how do we actually do reasoning about crypto using VCC? Well, that's what this is showing here. So this is the function signature for decryption in C. So this part here is sort of standard C. So decrypt takes a pointer to the key together with an int32 that's the key length, a pointer to the ciphertext together with its length, and an out buffer that it's going to write to. And it returns a result, an int32. And the idea is it's going to return 0 if it hits some error. So it's authenticated decryption, say. So it returns 0 if it fails. Otherwise, it will be a non-zero result. So that's going to be the length of the outcome that's been written into this out buffer. And so this is a contract, or a postcondition, which I mentioned earlier, that says that if the result of calling the function isn't 0, so there's not been an error, then it's the case that the original ciphertext, which was the thing we're decrypting, the in whose length is in len. So getTerm is a function that takes the current state. It's a stateful function that takes the current state of memory and interprets it as a $Yao term. It says that the term corresponding to that part of memory is an senc of the key and the resulting ciphertext. Sorry, the resulting plaintext. Okay, so So VCC doesn't know anything about senc and about getTerm and so forth, so we have to sort of program that up in VCC. And we wanted to do this we want to exploit the fact that the theory that we developed for F7 was actually language neutral, so we developed this theory in Coq, this interactive prover I mentioned earlier, developed at INRIA, that's for general purpose mathematics. And so we developed a nice general purpose theory of Delaunay algebra within Coq. And so this has got, so the next few slides have got nothing to do with C and could be applied to F#, could be applied to Java, you know, whatever you like. So the first thing we do is introduce a term algebra. And so for this protocol, it's very simple. We have literal byte arrays that represent keys or nonces. We have pairing of 2 byte arrays, or sort of injector pairing that can be reversed, and also authenticated encryption of a plain text with a key. Then we also want to keep track of events that have occurred. So we have a log, which is a set of events. So we define down here that the log is a set of events, and an event comes in 4 flavors, and we have a predicate logged that just says that an event E is in the log. So what are the things that can be in the log? The most basic thing is we keep track of new byte arrays that have particular usages. And the usage type is over here. And this is where we keep track of the fact that we've got that byte strings can be used as nonce or as senc keys. And then for each of those kinds of things, we have another type that is protocol specific that says, that describes the usages. So for nonces, a nonce can be used as a request or a response. So we include, if it's a request, the names of the principals. If it's a response, we also include the request that it was related with. On the other hand, a nonce might, a byte string might be a symmetric key, and in that case, there's 2 kinds of keys. There's a long-term key between A and B, which is RPC KAB between A and B, and there's also the session key that's specific to a particular request. And so we have a constructor that says that, or says just that it's an RPC session key with some data. Okay, so back to events. So what I was saying over here was just that, you know, every byte string that we introduce has an associated usage that's described over here, and that's partly protocol specific. And then also protocol specific, we have events corresponding to these guys here in the specification of the protocol, speaking about a request or a response, and also bad, indicating that 2 guys have gone wrong. So we can just type this into Coq. And then we build up an inductive definition of the kinds of terms that might arise. So I mean, a key idea, the purpose for this is that we don't want to allow any old symbolic terms to arise or in the protocol. I mean, they don't. I mean, the protocol proceeds in a certain uniform way, and so we want to capture that behavior in what's a bit like a type system, but we set it up as an inductive definition, a bit like a logical definition in Coq. And the key predicate is this level LTL that says that a term T is at level little l, like low or high, given the log L. And so we have a number of rules here that these are actually generic, but they're parameterized by operation or predicates like nonce comp and senc comp that are protocol-specific rules speaking about when a nonce might be compromised or a key might be compromised. And then there's also a rule for here for a parameter can senc, which is protocol-specific predicate that says when it's safe to, when you're allowed to encrypt a plain text with a particular key in a protocol. And what this rule here says is that it's fine if you have a plain text at a level high, so it's a plain text that's known to the user, to the compliant code, and it satisfies this precondition can senc kp, then you can allow that to appear at either level, in particular level low. So in particular, that means that this rule is, so the precondition for outputting anything on the wire is that it's at level low. Anything input or output from the network is at level low. And this rule here is the only way that I can turn a ciphertext or create a ciphertext or from a high plain text and allow it to be emitted on the wire. So what's can senc? Oh, I should say this work is this whole theory, this whole generic theory developed in Coq was originally in this paper with Karthik and Cedric at Popple.
So you can't encrypt something
you can encrypt. There's another rule for that, for this rule here. Yeah, you can encrypt things at level low, but you stay at level low.
Okay, yeah.
So there's no. So this rule says I can. This, in a sense, can be used to type the attacker or a sort of a bit of code that's gone wrong. Anything that's level low can also be encrypted and stay at level low. But this is the rule that governs when you can take something at high and sort of turn it into level low. So that. Okay. So can I say this is the precondition for encrypting in this protocol, and there's two rules. So it's either that condition applies or this condition applies. I'm not going to go through all of this, but this clause corresponds to encryption with the long-lived key, and this clause corresponds to encryption with the short-term key. And what it's saying here, and note this is all dependent on the log, the current state of the protocol run. What this says here is that if you, let me see, we're trying to encrypt plaintext P with the key K. It's saying that if the key K has been logged as being a key for a long-term session key between A and B, then it's okay to encrypt P if P is a pair of a request and a session key, it's this guy here, a request to the session key, so long as the request is in fact a fresh nonce for this run between A and B, and also that we've logged that we want to send this request from A to B, so that this line here corresponds to that. So it's kind of saying I can only encrypt this message if I've earlier asserted that I want to send a message. Okay, and that's important because we do a chain of reasoning back after we get a ciphertext. You know, once we've established that it was actually encrypted with this key, we can inspect this predicate and say, well, look, the only way we could have encrypted it is if this clause was true, and then that would mean that it must be that the request has been asserted in the log. And then finally, and if that's the case, then and additionally, it had better be that the other part of the pair, KS, is actually a session key. Okay, so that's sort of formalizing in logic what your intuition about the protocol, and then we can define some correspondence theorems, one corresponding to each message, and the correspondence theorem for message 1 says that if you've got a well-formed log, which is defined elsewhere, and you have a KAB that's a long-term key, and you actually have a ciphertext that's encrypted under KAB that's at level low, so it's on the wire. If you have all that, then either the session key has gone wrong, bad AB is in the log, or it's the case that there was actually a request, and the other guy in and the key is in fact a session. Yeah, the other guy in the ciphertext K. So it's saying the request is a good request. Another guy in the request K is in fact a session key. So these are sort of lemmas that kind of capture the behavior of the protocol, but we want to use them when actually reasoning about VCC. So this is, I'm going to quickly go through how we do the reasoning. So I don't expect you to get all of the details of this, but I hope you'll get some of the intuition. So this is the code we want to reason about. And note, so this is, this is actually after decrypting the, I think the first message, receive the response. No, this is after receiving the second message. So we have a bunch of code. We receive the second message off the wire. M2 is received off the wire. We do some stuff on it. We decrypt it. Or rather, we find various stuff about it. I'll find the actual length. Then we do a decrypt, and then we do an assert. And so this assert here corresponds to this assert over here. All right, so this is all phrased in terms of ghost state. So we assert that in the log that either, so that corresponds to that either there's a response that corresponds to this, or the log says that that one or other of the parties has gone wrong. So the policy is how to persuade VCC to verify this. So the first thing we do is we take all these theorems and axioms that have been proved in Coq. So we have this like consistent logical theory in Coq, and we import them as axioms into VCC, so we can use VCC to verify this code. And then we focus on this part of it, the receive, the decrypt, and then the assert. So after the receive, we get as a post condition that the term, the message 2, the term corresponding to message 2 in the concrete memory is at level low, and that's valid because that's our assumption that everything coming off the wire is at level low. And then after calling decrypt, so you remember I went through the contract for decrypt, and it said that if the length is non-zero, then we know that what you've got back is the symmetric encryption of the, or rather what you've got back is the plaintext that was in the symmetric encryption. So if we instantiate the postcondition I showed you of decrypt, you get this. And we note that it's only true because we've checked that the response wasn't zero. So we abort at that point. So this holds if we fall through after the if. So we know that the ciphertext that we received off the wire actually was this senc. And then we appeal to the theorem I showed you, theorem C2, which says that if you have a low ciphertext, then either the key's gone wrong or the response is good. And so this becomes an axiom to VCC, and it uses that to prove this. So this is just the same thing written out in VCC notation. So voila, we sort of complete that part of the proof. Okay, so that was a lot of detail about a wee example. So I hope you get the rough idea that we've developed the theory in Coq first of all, using its nice mechanisms for developing mathematical theories, and then we pull it over into VCC. And so VCC is great for reasoning about specific C programs, and we get it to maintain in its state, what can be deduced, the postconditions of everything that's happened so far, and use that to prove asserts. And so this slide is just giving some performance. So the interesting column is these ones here. So we had a couple of examples totaling about 450 lines of code. And in an initial publication at CSF last year, we had some quite high run times, and Francois worked really hard on reducing the run times, making it much more efficient. And so good on him. He's really got the run times down. So they're now within, they're just taking a few minutes, whereas before we had some really long run times that were kind of intolerable. So we've got this to a reasonable performance, and also reduced the number of lines of annotations. But still, you do need a fair number of annotations.
The annotations have to be manually added.
Yeah,
That's kind of where the skill still.
There is still a bit of skill. Yeah.
And it seems many examples, the lines of annotation equals the lines of C.
Yeah, it used to be worse though. Consider the alternative. Yeah, but that's not unique to this actually. I guess we knew that already. That there's been several applications of things like VCC and Framus C to a bunch of codes in C, and they all seem to have that kind of problem. So it's a good research topic, how to reduce the number of lines of code. Okay, so to summarize that part of the talk, this is very much Francois' work. We get full verification within VCC, but it does take more interactive effort, which is what we're just saying. I should call out, we do get full verification, but currently it's within the Dolomieu model. And we're not addressing timing or power consumption or physical attacks. I mean, that's an interesting topic to look at, obviously, but we're not currently do that. What we're currently doing, so in joint work with Cedric, we've been adapting to some computational assumptions, and that seems to be going quite well, but we're not there yet. And we're also looking at some of the code base of the TPM chip, which is a nice target for this kind of technology, in that the new version of the TPM, which is in many laptops, TPM supports things like BitLocker and other sort of functionalities, other kinds of trusted computing functionalities. And the new version of that is actually specified by a large chunk of code in ANSI C. So we're looking to see if we can verify properties of that. I wanted to say, I mean, we're not the only people to look at this. I mentioned CISO earlier. There was some early work around about that time, about 5-6 years ago, that looked at using symbolic model checking and looking at verifying protocol compliance, but not directly doing security. A much more substantial project was Aspire, that was done at CMU by Chaki and Data, and they were able to prove results about the main loop of OpenSSL, but to do so they did a lot of abstraction about what other subroutines that were called from the main loop were doing. I mean, we really only abstract the behavior of crypto operations, but they were abstracting much bigger chunks of code. So bottom line, to date, I mean, this is still quite an open area that, the state of the art is still relatively few lines of code and makes quite big assumptions. Tales from the war on error. I'm sort of running out of time, so maybe I shouldn't dwell too long on this. But you know, I'd say, you know, we're in a war here, you know, against, you know, problems in computer software, and we've been taking the war to cryptographic software. I'd say, well, symbolic execution is great, but we've not yet found how to scale it beyond or adapt it beyond multipath analysis. General purpose verifiers are good, but they have a huge annotation burden. And I find this super frustrating. I keep saying this to various people, but there are a number of tools that can prove things like memory safety automatically of C code, but it seems very hard to get to get the output of those tools and feed them into things like VCC. So already I was taking the output of Coq and importing it as axioms into VCC, meaning that I had much less work to do in VCC. You know, I could do the mathematical development in an environment that was well designed for it. I'd like to do the same thing with memory safety. So that at present, you know, we have to do a lot of work persuading VCC that the code actually is memory safe, which has got nothing much to do with the cryptographic security of the protocol. Well, it's part of it, but it's not the only thing. And it's really frustrating because there are lots of tools that can find such problems, but it's hard to get them to produce a suitable output that I can import into VCC. So, I mean, I think that's a nice research area for things like, for that class of prover. You know, how can it make use of the outputs of automatic tools? Okay, we have, very quickly, CSEC challenge. We were frustrated by the absence of small numbers of, you know, small chunks of code that one could try out these techniques on. And so we've launched a website last year called the CSEC challenge, where we're collating a bunch of small examples of, and large examples actually, of cryptocode in C, and putting them up for the research community, both in cryptography and in program verification, to see if we can find faster and more efficient techniques, you know, more automatic techniques to verify properties of them. So let me conclude with that slide, and I will be happy to take questions. Thank you for your attention.
Any questions or comments?
As far as I understand, you feed into your checkers C code, and it will tell you whether the code, once executed, will result in a secure protocol somehow. My question is, don't you mix two unrelated topics there? Wouldn't it be cleverer to first specify somehow the specification of the protocol, what it should do? So, like start an encryption block cipher, initialize a block cipher, generate a key, use it like in this way. Then you compare, then you verify using these or related methods that the C code actually implements the specification. But you leave out all security considerations, and you define the code as good if it is if it implements the specification. And then with different tools, you can analyze the specification, and then you don't have to deal with all these problems.
Right. Well, there's two responses. One is like, where do you get the original specification? And we've, I guess at Microsoft, we've spoken with protocol designers, you know, a lot, and we find that they never write down specifications. You know, you get PDFs, but you never get anything that would. People are not sitting down writing proverb, you know, descriptions of their protocol. You know, so part of the point of looking at implementation code was that the early implementations of protocols are up on the first and only time these things ever get formalized. So we wanted to have techniques that could take those. I mean, there are formal descriptions, not very malleable formal descriptions, and extract something we could verify from, you know, from them. So that's very much what Misha's been doing with the symbolic execution that we're saying. The idea is you've got a new implementation like the smart meter. It's the first and only description, formal description of it. So let's see if we can extract something from it and then analyze it. The other response is actually, well, is to say that, I mean, yeah, I agree, separation of concerns is good. And in a sense, that's what we've been doing, because the Coq theory I described is, in a sense, is a description of the protocol independently of the particular code. You know, by the time you've been, so we've got a general framework there in Coq, you know, and it was parameterized by things like rules for when nonces can be compromised, for the precondition of encryption and a precondition of signatures and so forth. And by the time you specify what those preconditions are, you've essentially got an abstract description of what the protocol does. And the theorems I had in Coq, the C1 and C2 theorems, essentially were correctness properties of the abstract description. And then the second part, you know, when I was inside VCC and doing a little bit of local reasoning, that's essentially where I'm saying, I'm taking the general correctness theorem that has been proved abstractly and then instantiating to the C code. So in a sense, we are doing what you suggest.
Talking about things you're linking tools together, I wonder if that kind of relates to the PBS guys talk about as being kind of like a tool bus where they've got things like theorem provers and model checkers and SMT solvers, and the idea is you want to be able to do parts of the problem or different parts of these and link them up together, and that's kind of sort of the obvious missing component. It's sort of a similar thing here, where you really want to be able to take stuff out of one tool and put it into another.
Yes. Yeah, very much. I mean, that's where we get progress, when one automated tool meets another.
Any?
I'm puzzled by your last point that you say that you're moving towards verifying substantial crypto implementations. From your talk today, I very much got the impression that you're moving towards verifying substantial protocol implementations with a symbolic view of cryptography still. Is your approach actually now really looking at the crypto layer, or is that still abstracted away as a library or some kind of?
I'm only speaking here about work that's finished and written up, but in recent work we've been looking at using VCC to do computational proofs. I mean, we're taking the work that Cedric has pioneered using F7 to do computational proofs about F# code, and we've moved that into the world of C.
Okay.
And so we've got a version of the TPM with a sort of computational style specification as a sort of ideal functionality, and then we're showing that the C code implements that, or showing correctness with respect to that.
Okay, any other comments? Okay, let's thank the speaker again.